and welcome to CodeChef. In today's video, I'm going to be discussing a problem: is sum possible? The code of this problem is POSLS1. So do go to CodeChef's practice problems and look this code up and try to solve it. And then if you are unable to, you can come back to the editorial and I'm here to explain it. The prerequisites that you're going to need for this question are mathematics, precomputation, as well as subarrays. Precomputation is going to be a major part of this because the constraints are going to be pretty less. So apart from that, we are going to be using brute force itself. The difficulty of this problem is Cakewalk. So let's take a look at the problem statement and get started with it. Problem statement says that you are given an array A of n integers as input. You are also given an integer q, that is the number of queries. In each query, you will be given an integer x. You have to find the number of subarrays of A having sum exactly equal to x. So let me explain this with some doodling. You're going to be given an array A of length n. So if we use zero-based indexing, the indices would look something like this all the way up to n minus 1. You're also going to be given a number q followed by q queries. So let us say if we store this in an array q, these queries in an array q. So this would look something like this. So we are going to be given these two things and we have to find for each query, that is for each query we have to find how many subarrays in A give the sum exactly equal to this x. That means exactly equal to the current query that you are traversing or taking as an input. If I try to explain this with an example, let us just take a look at the example that is given in the question itself. So the example given to us is n being 4, the array being 2, 3, 0, 2, q being 2, and the queries are 10 and 5. Now for 10, we have to look for a sum that is equal to 10. How many subarrays in this entire array give us a sum that is equal to n? Is equal to 10. So 3 plus 2 is 5 and 5 plus 2 is 7. So the maximum sum that we can obtain from this array is 7. That means 0 number of subarrays give a sum of 10. So the first answer for this would be 0. That is the count of subarrays that give a sum of 10. The second sum is 5. How many subarrays in this give us a sum of 5? So the first one that you can observe is this 3 plus 2, which will give you a 5. So this would be the first subarray that gives a sum of 5. So the count of subarrays, let us make it 1. Let us assume that initially it was 0 and now we've made it 1. Now the other one that can give us the sum of 5 would be this 3 along with this last 2. So this also will give us a sum of 5. 3 plus 0 plus 2, that is 5. So now the count of this becomes 2. Is there any other subarray that can give us a sum of 5? 3 plus 0, 0 plus 2, 2 plus 3 plus 0. So there you see another one that we have not yet circled, right? So 2 plus 3 plus 0 would also give us a sum of 5. So that makes it a total of 3 subarrays that give us a sum of 5. I don't see any other subarray here, so that is going to be the answer, 3. So let us check. First one gave the answer of 0 and the second one gave the answer of 3. So this is what we have to find. I hope the problem statement is now clear before we move on to the explanation, the logic and algorithm. Let me make the array again. So to find a subarray, if I use brute force and traverse over all possible subarrays, how much time would that take? Let us say I have n number of elements that are given to me. How many subarrays can be found in this of different lengths? So the first subarray would be this. Let's say the second subarray would be this, but the subarrays ending at index 1 can also consist of only index 1. So that would be another subarray. The third set of subarrays that I can look at is all the way from 0 to 2. The other one can be from 1 to 2 and then only 2. So I hope it is evident which one my line is corresponding to, which index my line is corresponding to. So what I'm doing is I'm finding all possible subarrays that end at a particular index. So if I look for subarrays that end at index 0, the subarray is going to be from index 0 to 0. If I look for subarrays that end at index 1, the subarrays are going to be 0 to 1 and 1 to 1. If I'm looking for subarrays ending at index 2, then I can write them as 0 to 2, 1 to 2, and 2 to 2. So we can observe a pattern over here, right? The index at which we are trying to end the subarray, that would be the last index of starting of a subarray as well. And we will keep decrementing it all the way up to 0. So that means for any index x, the total number of subarrays that we can check to find the sum is from 0 to x, 1 to x, 2 to x, all the way up to x to x. So this is the pattern that we were looking for. Now that we've found it, we can use this information to build the algorithm further. Since I'm given q queries, what would happen if if I check for all of these subarrays for all q queries? The limit of q that is given to me is 10 to the power 5. N is given to me as 100. I'm writing down the maximum value so that I can analyze how much time would my code take if I check all possible subarrays for all q queries. So N is given to be 100. Maximum A of I maximum is given to be 100 as well. And X is given to be up to how many zeros are there? 1, 2, 3, 4, 5, 6, 7, 8, and 9. So all the way up to 10 to the power 9. Now, since all of the numbers in AI are positive, we can never obtain a subarray with a negative sum, which is why x being equal to minus 10 to the power 9, as is given in the constraints, will not really bother us a lot. All right, so we were checking the complexity that we would obtain if I was to find the sum of all possible subarrays for all q queries. So if we consider that we are traversing each element to find the sum of a subarray, we would have to traverse n elements to find all the subarrays with just one element in them. So this would take me n time. I'm just listing the time over here. If I want to take a look at all subarrays of length 2, there would be a total of n minus 1 such subarrays, because the first one would be starting at 0 and the last one would be starting at index n minus 2, ending at n minus 1. That's why we'll have one less than the number of arrays that we had to check the previous time. But also in this, the size of the subarray is 2, which means for each of these n minus 1 subarrays, we are going to have to traverse 2 indices to find each sum. So that's why n minus 1 into 2 becomes our complexity for finding sum of all subarrays with length 2. Similarly for 3, with the same logic, it would look something like this. For 4, it would look something like this. So if we go all the way up to subarrays of length n, because that's the biggest subarray that you can obtain, which would be equal to the entire array itself, this would make it n minus size of the subarray minus 1, size of the subarray minus 1 times the size of the subarray size of each subarray itself. So instead of this, I can just write it as 1 times n. Now a sum of all of these numbers would give me the total complexity of finding all possible subarrays for a single query. And q times the sum of this would give me that for all q queries if I were to find sum of all subarrays for each query separately. So the sum of all the elements resolves into something which gives us big O of n cube time complexity. So I've written the solution over here. Okay, I'll just go over it instead of telling you all to look it up. Right, so the equation that we ended up with was the sum of n plus n minus 1 times 2 plus n minus 2 times 3 and so on. So if I expand this, I can divide it into two parts. One that makes up n plus 2, n plus 3 and all the way up to n times n. And the other, which is the negative part, and it is made up by 1 times 2 plus 2 times 3 plus 3 times 4 all the way up to n minus 1 times n. Now, 1 times 2 plus 2 times 3, this entire sequence, it actually can be proved that this has a sum by induction, which looks something like this, n times n plus 1 times n plus 2 entirely divided by 3. And the first one is just if we take out n common from this entire equation, it is just sum of the first n natural numbers. So that would be n times n plus 1 by 2. And the common n that we took out is over here. So now this is a pretty simple equation to solve, right? So you can easily see that this comes to this equation and then this gives us a big O of n cube complexity. Now, like I said, for this is just for calculating all possible subarrays sum just one time. If we look into calculating this for all q times, this would give us a complexity of qn cube. Q has a value of 10 to the power 5 and n has a value of 100. Now 100 cube is 10 to the power 6. So 10 to the power 5 times 10 to the power 6, which means 6 plus 5. So 10 to the power 6 plus 5, 10 to the power 11. Now 1 second is of 10 to the power 8. So if I divide this by 10 to the power 8, this would give me 10 to the power 3. That means this code would run for 1,000 seconds if I were to approach it this way. However, we are aware that once we have found all possible sums for all possible subarrays, we know that the array is not going to change for all q queries. So we don't need to recalculate the same sums all q times. If we calculate it just once, that would suffice. So that would lead us to a complexity of q plus n cube. Now since n cube is just 10 to the power 6 and q is 10 to the power 5, this would give us a complexity of maximum of these two. That means O of 10 to the power 6. And since 10 to the power 6 divided by 10 to the power 8 would be 0.01, yeah, 0.01 seconds. This is less than 1 second, which is the time limit given for the question. So we can definitely do this approach. So this would be the brute force sort of approach. I'll just code it out and then I will tell you about an approach which would just give us an answer in n square instead. So I'll remove the code and code it again. So the code I just opened was for n square complexity and we will go back to that once we are done with this sort of a brute approach. So the first thing I do is declare n and take the value of n in my variable n. Then I have to declare an array in which I will take all the values of the given array A, these values. So I will use a for loop for this. Now I need to calculate sums of all possible arrays. So instead of appending all of these sums into a vector or something like that, all we need is the count, right? Let me clear the board. All we need is the count of subarrays with any particular sum. So what we can do is, suppose if I find a subarray with a sum of 100, I can use an array in which on the 100th index I can increment this previous value by 1. So if I initially had x subarrays which were giving me a sum of 100, now I can increment it by 1 because I have just found a subarray that gives me a sum 100. So this way I will be storing the count of subarrays that give me a particular sum. How many sum values should I be doing this for? So AI is given to be 100, even though the sum that that the query can ask us for is 10 to the power 9. We don't need to have an array ranging from 0 to 10 to the power 9, because it is never possible in our array to have a sum which is equal to 10 to the power 9. This happens because of the value of AI that is given to us. So AI's maximum value is given to us as 100, and the maximum value of n is also 100. So what can be the worst case? If all the elements in my A are equal to 100, then the sum of the entire array would be 100 times 100. That means 10 to the power 4. Can I ever, in any test case, have a sum of any subarray that will be greater than this? No, because if this is the sum of the entire array, in the worst case, then any subarray of that worst case array would be less than this. And any array itself which is not the worst case would also have a maximum sum less than 10 to the power 4. So this is why we are only going to need an array in which we store the sums. By store I mean increment, the approach of incrementing. So we only need an array in which we can increment the count for sums extending up to 10 to the power 4. So there can be a sum 0, there can be a sum 1 found in any subarray, there can be a sum 2 of one of the subarrays, and the worst case is that the sum would be 10 to the power 4. So we only need to have an array with 10 to the power 4 cells. Now in my original array A, this is my, I'll call this sums array. Now if in my array A, I'm looking at this particular section, let's say, and it has 1, 2 and 3 in itself. 3 plus 2 is 5 and 5 plus 1 is 6. So I'm looking at a sum of 6 now. So in my array up top, what I will do is I will increment the count of arrays that give me a sum 6. So sums is storing the count of arrays that give us a sum equal to the index. This is what my sums array is going to do. Now when I receive a query queue, all I have to do is output that particular count for this query. So if it is queried that the judge wants me to tell how many subarrays in this given array A, have a sum of 6, then all I have to do is output this value, sums of 6, because I have stored the count of total subarrays which were giving me a sum 6 in this already, at this index already. So each query would take O of 1 time. This is how we are doing this. Now moving back to the code. So I'm doing a little bit of back and forth here because even though it is a simple question, explaining it can be a little bit tricky at times. So once I have taken all my values inside the array itself, like I said, I'm going to need an array sums to store sums all the way up to 1000. I'm sorry, 10,000. They're all going to be initialized by 0 because initially I don't know any subarray with any sort of a sum. Now here note that I'm not trying to make sums of 0 as 1, because you must be wondering that a subarray that has no element will have a sum of 0, right? But a subarray will only be a subarray when it has at least one element. That means at least one cell included. So that's why all possible sums, are initialized with a value of 0. Now for the brute force approach, what I have to do is start with every index possible and end with every index possible that is after this index that I'm currently at. So I'm using a variable j for that. The least length subarray that can exist in the entire array is of length 1. That means something that starts at index I and ends at index I as well. That is why my j, that is the ending point of the subarray that starts at index I, is going to be I at first, and then I'll go on incrementing it all the way up to n. So that is what I'm doing in this loop. Now I need to find the sum of subarray starting at index I and ending at index j. So I will use another loop for this. I will also need a variable to store this sum, so I'll declare that and initialize it with 0, because initially there is no element that I have traversed. Now that I'm traversing the ith element, I plus 1th element, I plus 2nd element, and so on up to the jth element, I will add all of these to the sum. So k is representing that index of the element that I'm traversing. That is why I've added it to su. So my variable that was storing the sum, I have added a of k to it. Once I've found out the sum, I can increment the count of subarrays with a sum equal to su. And that is what I'm storing in my array sums. That is why I'm going to increment the su valued index of the array sums by 1. Also, since the maximum sum that I can attain is 10 to the power 4 and the minimum is 0, I would need my last index to be 10 to the power 4. So my length should be 1 greater than that. So I have made that correction over here. Now I need the queries. So I'm declaring a variable for that, take that variable in, run a loop to take all the queries. Oh, okay, I'm sorry for that. So take the variable in, run a loop. So I'm taking in each of these queries. If this query is greater than 1000, then the answer will always be 0, right? Because it is never possible to have a sum greater than 10,000, and we have already discussed this. So pardon me for saying 1000 earlier, it is 10,000. So if the query that I have received is greater than 10,000 or it is negative, since there is no negative element in my array, this is also given in the constraints. That means if the sum that is queried is negative, then in both these cases, the output would be 0, because there will exist no such subarray. Otherwise, if it is between the values of 10,000 and 0, both inclusive, then I will just access that index of the array sums and output that, because this will give me the count of all subarrays that have a sum equal to q0, which is my current query. So as you can see, there are 3 loops running over here. One is from 0 to n, the other is from I to n, and the next one is from I to j. So you can analyze it just by the code also, that the complexity would be big O of n cube. We have already done this theoretically. So, okay, I raised that part, but we have already done this theoretically. You can go rewind the video a little bit and you'll see that we had already calculated that big O of n cube would be its complexity. So this code, according to me, should work. Let us see if it works. If it doesn't, we can debug it together. So it gives a correct answer. However, let us note this time complexity. So this complexity is 0.17 seconds in this case. I'm just doing this so that I can compare it with the big O of n square approach that I'm going to show you guys now. So yeah, big O of n cube approach gave us 0.17-second runtime. Now we need to find out that for n squared approach, and we can, so that we can compare it. It's not something necessary because as we know how to calculate the complexity, I don't think that the actual runtime matters, but I want you all to practically be able to compare the runtimes. That is why I'm mentioning these. So now if I want an approach in which I am solving this in n square, an observation that I can make is that when I'm running a loop from I to j, if I'm running a loop from, let's say, 1 to 3, then that means just before it, the value of my j was 2. So I would have had the value of 1 plus 2 in the last iteration. But in this iteration, I'm again trying to go from I to j and find the sum. Why can't I use the previous value that I had already calculated and just add the newer value of j to it? I can do that, right? So this will help me not iterate over the same thing and find the same sum over and over again. Now, this is also called as prefix sum. So usually in a lot of codes, you will have use of a prefix array, which means if you originally have an array, you're going to calculate the sum of each prefix in another array. So for example, the prefix 0, then the prefix 01, then the prefix 012. So such an array is very useful in some of the questions in competitive programming. You will figure this out as you do more problems. However, in this case, we don't need an entire array because the previous value that was calculated by us is going to be the prefix itself. So now we can just remove this sum from here and declare it over here instead. So we would not need this third loop now. So what is happening is if I start from I equal to 0, the value of my sum is 0. J starts from I, so it will start from 0 as well. Now I will add this 0th one in this, since I don't have a kth index. I will add aj to this sum and increment the count of arrays that have a sum equal to su, because the prefix is a subarray itself, right? After this, I increment j. So now the size of my subarray that I'm traversing has increased by 1, and one element only has increased in it. So I only need this newer element to add into the value of su, because I already have the value of the prefix from the previous iteration. So this is how I'm doing this now. The rest of the code obviously remains the same. So let us see if this code works. If it doesn't, we can again debug it together, right? So this gives a correct answer. The runtime is about the same, 0.17 second, as we had received in the previous one as well. Now, one possible reason for this can be that there are not test files big enough. So no problem. Let's not get into the specifics of how things are happening at the backend. I just hoped that it would give a lesser time so that we can actually compare. Well, it doesn't matter. Anyways, its complexity is still going to be less than the previous one. So we did the previous one in n cube, and this one we did it in n square. So that's about it for the code, I think. Now let's move on to the common mistakes. So one of the common mistakes that I noticed was to recalculate this entire sum of all the subarrays possible for all Q queries. So this won't give a wrong answer, but it will give a TLE verdict, because like we saw, the time was coming out to be somewhere around 100 seconds, I think. So yeah, you can go back to that part of the video where we discussed this first approach, where the time was coming out to be way more than the time limit of the question, which was 1 second. So that's one prominent mistake that I found. Another one is getting a runtime error. So I'll just show it to you live. Even I made that mistake once, so it must be lying in my submissions. That's why I told you that I'll show it to you live. So there you go. So in this case, I have not checked whether the index that I'm accessing, that means the current query that I'm going to access, whether it is within the bounds of my array sums or not. So this was checked in the earlier code, the code that we submitted. This particular statement, it was to check whether the sum that I'm accessing is within the bounds of indices of the array sums. If it is not, then I'm outputting 0, right? Now if you don't check this, then you will get a runtime error, because the queries can be negative as well, and if you go ahead and access a negative index, that's not going to be possible by the language, so you will receive a runtime error. That's also another error that I encountered in a lot of codes and in my own code. So that's about it for today. Thank you for watching, and I'll see you next time.